Semiconductors like silicon are pivotal for manufacturing electronic circuits. These materials exhibit diverse properties including preferential current flow, variable resistance, and sensitivity to light or heat. Silicon, germanium, gallium arsenide, and elements near the metalloid staircase on the periodic table serve as examples of semiconductors. Gallium arsenide, the second most prevalent semiconductor after silicon, finds application in laser diodes, solar cells, and microwave frequency integrated circuits. When areas with varying doping levels coexist within a crystal, they establish a semiconductor junction, the foundation for diodes, transistors, and most contemporary electronics. Through doping and the application of electrical fields or light, semiconductor devices can be utilized for amplification, switching, and energy conversion. Semiconductors also find application in high-capacity, medium to high-voltage cables for insulation purposes, typically employing plastic XLPE with carbon black. The conductivity of silicon, for instance, can be enhanced by incorporating minute amounts of pentavalent or trivalent atoms through a process referred to as doping, resulting in doped or extrinsic semiconductors. Furthermore, elevating the temperature of a semiconductor can boost its conductivity. This contrasts with metals, where conductivity decreases with increasing temperature. Semiconductors are materials that possess a level of electrical conductivity between conductors and insulators. By introducing impurities to their crystal structures, their conductivity can be altered. The contemporary comprehension of semiconductor characteristics relies on quantum physics to elucidate the behavior of charge carriers within a crystal lattice. Doping significantly amplifies the quantity of charge carriers in the crystal, with group V elements creating free electrons, N-type doping, and group 3 elements generating free holes, P-type doping. Semiconductor materials utilized in electronic devices undergo precise doping conditions to regulate the concentration and distribution of P and N-type dopants, resulting in P-N junctions responsible for the device's operational features. By utilizing a hot point probe, distinguishing whether a semiconductor sample is PP or N-type can be swiftly determined. Notable advancements in semiconductor properties were documented from the mid-19th to early 20th centuries, culminating in applications such as the development of the cat's whisker detector in 1904, marking the early practical utilization of semiconductors in electronics. Quantum physics breakthroughs subsequently led to the creation of the transistor in 1947 and the integrated circuit in 1958. Semiconductors can exhibit variable electrical conductivity by undergoing processes like doping or gating, resulting in N-type or P-type materials based on the surplus or deficiency of electrons, respectively. Combining differently doped semiconducting materials gives rise to homojunctions, fostering the exchange of electrons and holes until equilibrium is achieved through recombination, forming an electric field across the junction. Disruptions to thermal equilibrium in semiconductors introduce excited electrons and holes, leading to ambipolar diffusion. This disturbance, induced by factors such as temperature variance or photon exposure, causes generation and recombination of electrons and holes in the material. Certain semiconductors emit light when excited electrons relax, a property harnessed in light-emitting diodes and fluorescent quantum dots by controlling semiconductor composition and electrical current. Semiconductors with high thermal conductivity are integral for heat dissipation and enhancing thermal management in applications like electric vehicles, high-brightness LEDs, and power modules. Semiconductors with high thermoelectric power factors are valuable in thermoelectric generators, while those with high thermoelectric figures of merit are used in thermoelectric coolers, highlighting their significance in thermal energy conversion. A vast array of elements and compounds exhibit semiconducting properties comprising certain pure elements located in group 14 of the periodic table, notably silicon and germanium, due to their possession of 4 valence electrons in their outermost shell. This characteristic allows them to readily gain or lose electrons. Additionally, binary compounds like gallium arsenide and ternary compounds, oxides and alloys, alongside organic semiconductors and semiconducting metal organic frameworks, are notable for their semiconducting attributes. The prevailing semiconducting materials are typically crystalline solids, although amorphous and liquid semiconductors are also identified, encompassing hydrogenated amorphous silicon and various mixtures of arsenic, selenium, and tellurium. These compounds share properties such as intermediate conductivity, sensitivity of conductivity to temperature changes, and occasional negative resistance. Despite lacking the rigid crystalline structure of traditional semiconductors like silicon, these disordered materials are commonly employed in thin film structures due to their resilience to impurities and radiation-induced damage. In the preparation of semiconductor materials for integrated circuits, ICs, chemical purity is of utmost importance to ensure optimal performance. Even minor imperfections can significantly impact the behavior of semiconducting materials given their scale of application. Moreover, a high level of crystalline perfection is necessary as faults in the crystal structure, like dislocations and stacking faults, can impede the semiconducting properties. Crystal ingots with diameters ranging from 100 to 300 microns are utilized in current mass production processes, typically grown as cylinders and sliced into wafers. The round-shaped characteristic of these wafers is achieved through the utilization of single crystal ingots, often produced using the Czochralski method. A combination of processes is employed in the preparation of semiconducting materials for ICs, including thermal oxidation for gate insulator formation, photomasks, and photolithography for generating circuit patterns, plasma etching for precise etching, and diffusion, doping, to imbue semiconducting properties characterized by the creation of a p-n junction. Semiconductors are distinguished by their unique electrical conductive behavior, positioned between that of conductors and insulators. The quantum states for electrons within these materials play a pivotal role in their conductivity, with delocalized states containing electrons necessary for electron transport. The energy levels of these quantum states are critical, requiring a state to be partially filled near the Fermi level to enable electron transport. Metals boast high electrical conductivity by possessing numerous partially filled states in proximity to their Fermi level. In contrast, insulators contain few partially filled states, with their Fermi levels situated within band gaps offering limited states available for occupation. An intrinsic semiconductor characterized by a band gap smaller than insulators demonstrates increased electron excitation across the band gap at room temperature. Doping and gating are techniques used to enhance and regulate the conductivity of semiconductors, expanding the number of partially filled states by moving the conduction or valence band closer to the Fermi level. Furthermore, wider band gap semiconductor materials referred to as semi-insulators exhibit electrical conductivity akin to insulators when undoped, yet can be doped to function as semiconductors. The generation and recombination of electron-hole pairs, essential for semiconductor behavior, are influenced by ionizing radiation and thermal energy. Doping, a process of introducing controlled impurities to a semiconductor, enables modification of its electrical conductivity, with donor impurities leading to N-type semiconductors and acceptor impurities resulting in P-type semiconductors. Through strategic doping and gating, semiconductors can be tailored to exhibit desired electrical properties conducive to various electronic applications. The history of semiconductor understanding traces back to experiments in the 19th century when various properties like time-temperature coefficient of resistance, rectification, and light sensitivity were discovered. Notably, Carl Ferdinand Braun created the first semiconductor device, the crystal detector, in 1874. Observations by various scientists contributed to the knowledge, such as Thomas Johann Seebeck noticing special characteristics of semiconductors in 1821, and Michael Faraday reporting the behavior of silver sulfide resistance decreasing when heated in 1833. Theoretical developments progressed with milestones such as the establishment of the band theory of conduction in 1931 and the work of Walter H. Schottky and Neville Francis Mott on metal semiconductor junction characteristics. By the late 1930s, Boris Davidov's theory on the copper oxide rectifier highlighted the importance of the p-n junction and minority carriers in semiconductors. The refinement of material purity in the 1920s led to improved experimental results and paved the way for modern semiconductor refining techniques, achieving parts per trillion purity levels. Practical applications started emerging with pioneers like Alexander Graham Bell, utilizing selenium's light-sensitive property for sound transmission in 1880, and Charles Fritz constructing a solar cell, albeit low in efficiency, in 1883. Progress continued with the development of devices such as point-contact microwave detectors and power rectifiers using copper oxide and selenium. The era preceding World War II saw advancements in infrared detection and communications using lead sulfide and lead selenide materials. The transistor era began with the breakthrough of the bipolar point-contact transistor by John Bardeen, William Shockley, and Walter Brattain in 1947 at Bell Labs. This development marked a significant milestone in semiconductor history, providing a solid-state amplification capability that was previously lacking in detector and power rectifiers.